it provides the precursor for phosphocreatine to bind through CK to produce ATP again. So you can appreciate then that the activation of this system is extremely sensitive to ATP demand. So ATP demand will be directly proportional to exercise intensity. So the sensitivity means how basically quickly it turns on. Right? If you're very sensitive to allergens, you don't need to be around a cat very long where you start sneezing or you have an allergic reaction. If you're not particularly sensitive, you can sit there and lick the cat if you want to, and you're never going to get an allergic reaction. So the sensitivity here is that the ATP demand it's very sensitive to ATP demands and can be activated very quickly through this rapid reaction. And it's a reaction catalyzed by creatine kinase. So those are kind of the core characteristics of this system. The role, as you can imagine then, is to supply ATP at the immediate onset of exercise to try to maintain that internal homeostatic regulation, to try to maintain or protect ATP concentrations at the level of the muscle, to supply ATP at extremely high rates for high power output activities. So again, because it's extremely fast, and the other energy supply systems are a little bit sluggish and need time to turn on and activate, this allows for very high power output activities. Okay, so for example, like a squat or something like that, or a 1 RM bench press as an example. Very high power output, short duration activities. And it really serves as an energy buffer and a precursor while other ATP supply systems are activated and turned on. It actually serves as the precursor to the activation of those supply systems. So you need this extremely rapid rate of reaction to signal glycolysis to activate, and glycolysis needs to be activated to kind of signal the activation of oxidative phosphorylation. So they're all kind of turning on together. The limitation, of course, is that there's a limited substrate, including stored ATP and intracellular phosphocreatine levels. So we run out of energy very, very quickly on this energy source alone. So it's great for high intensity, short duration exercise, but it can't be sustained. So I think a good analogy is essentially this ATP PCR system provides the energy for short-term intense exercise like a 100-meter sprint as an example. But an analogy is basically, it's kind of like, it's not much more effective than the car battery, which has just enough stored energy to turn the alternator to turn on the car. But you can't drive very far on the battery alone. You need to activate the cylinders to run the car in a sustainable manner so you can get to where you need to go. So it has just enough stored energy to get the system going, but it can't support the function of that system for particularly long. So, the next system that we have is glycolysis. So, I'm sure you've all, again, there's much more complicated pathways of glycolysis than this. But glycolysis is the anaerobic lactic system. And glycolysis basically is, again, the conversion of energy through glucose in the blood or glycogen in the muscle. So, this conversion of glucose to G6P occurs in the presence of hexokinase and F6P into this F16B, I forget what they're called to be honest, occurs in the phosphocreatine, phosphofructokinase as an enzyme. So the characteristics of glycolysis is that it occurs in the sarcoplasm and again has a very rapid rate of ATP production. It has both an energy investment phase, so it requires some energy to modify the structure of glucose and glycogen. So it has an energy investment phase. So glucose glucose is the precursor to glycolysis, it requires 2 ATP, and if it's glycogen, it requires 1 ATP to add phosphate to glucose and to fructose 6-phosphate. Right? So we require ATP as energy to transform glucose and G6P. It also has an energy generation phase where the net gain of glycolysis is 2 ATP if glucose is the substrate and 3 ATP if glycogen is the substrate. So From these two G3P molecules that are formed, we produce 4 ATP in the energy generation phase. But basically, if we're utilizing glycogen, we have to burn 1 ATP to transform that molecule. And so the net production is 3 ATP. If it's glucose, we have to burn 2. So the net production is 2 ATP. So ultimately, the role of glycolysis, again, is to supply ATP at high rates for high power output activities. So it's fast, it generates high power very quickly. Supplies ATP in the absence of adequate ATP through oxidative phosphorylation. So if oxidative phosphorylation basically can't keep up, if the metabolic enzymes are not elevated or are not active enough, if there's not enough oxygen in the cell, or some combination thereof, glycolysis will protect the muscle and provide the necessary ATP to produce the necessary force. But it does come at the expense of something, which is metabolic byproducts that can be fatigue causing. And ultimately, it's the first step in the aerobic degradation of carbohydrate, because ultimately, the breakdown of glucose and muscle glycogen produces pyruvic acid. And so pyruvate then can ultimately be transported into the cell through pyruvate dehydrogenase, converted to acetyl-CoA, which would then enter into the electron transport chain in the Krebs cycle, producing the reducing equivalents and the energy needed to drive oxidative phosphorylation. So as you can see already, glycolysis is actually the precursor for kind of the carbohydrate supply of oxidative phosphorylation. The limitation ultimately, though, is that it produces acidosis. So one of the byproducts of glycolysis is that pyruvate ultimately has 2 fates. Again, it can be utilized and moved into the mitochondria and utilized by the electron transport chain, or in the presence of lactate hydrogenase, can be converted to 2 lactate ions, or 2 lactic acid molecules, which then will rapidly dissociate into a lactate ion and a hydrogen ion. And it's that hydrogen ion in the cell which will decrease the pH or increase the acidity and compromise muscle function. So, it's very good for fast turnover of ATP. It produces quite a bit of energy, but it does come at the expense of acidosis, otherwise known as lactic acidosis. So, for the chemical reactions of glycolysis to actually continue, and to continue producing the reducing equivalents that are necessary for oxidative phosphorylation in the form of NADH, these 2 hydrogen ions must be removed from glyceraldehyde 3-phosphate. So ultimately, the hydrogen ion acceptor in this particular reaction is NAD. And NAD will accept the hydrogen ion and then will be converted to its reduced form, which is NADH. So this NADH ultimately generated during glycolysis must be converted back to NAD for glycolysis in order to proceed. So this NAD will accept the hydrogen ion from this G3P, produce the reduced form of NADH, which is NADH relieving a hydrogen ion in solution. But in order for this G3P to continue to cycle and to continue to produce ATP, it needs to be converted back to NAD. And so this is accomplished in a couple of different ways. So NAD is ultimately reformed to NADH. So through in one of 2 different pathways. So one is through a shuttling mechanism. So if there's sufficient oxygen available in the mitochondria to actually accept these hydrogen ions, that in the form of NADH, then the hydrogen ion from NADH can actually be transported across the mitochondrial membrane through 2 different shuttling systems, the details of which are not particularly relevant right now, but they're the malate aspartate system, shuttle system, which occurs primarily in the heart, and the glycerol phosphate system, which occurs primarily in the skeletal muscle. And these will ultimately shuttle the NADH into the across the mitochondrial membrane, which is relatively impermeable to NADH, and then ultimately for use in the electron transport chain to produce that electrochemical gradient necessary to drive BUTC, and ultimately then oxidative phosphorylation. If there is insufficient oxygen in the mitochondria, this is a little bit of a misnomer, but if there's insufficient oxygen in the mitochondria, or and more specifically, if mitochondrial activity is low, okay? So if, for example, say you've got plenty of oxygen in the mitochondria, but say the mitochondrial enzymes are sluggish, okay? They're not particularly active for whatever reason. Mitochondrial activity will be compromised, okay? Or if the rate of glycolysis, say during very heavy intensity exercise, is very high, and the enzyme pyruvate dehydrogenase cannot convert pyruvic acid that's produced through glycolysis into acetyl-CoA at a rate fast enough to be utilized by the electron transport chain. So in other words, if pyruvic acid is produced through glycolysis at a faster rate, then it can be utilized by the mitochondria. Either because the rate of glycolysis is so high and so much pyruvate is being produced, or because the mitochondria are slow and not particularly active. Pyruvate either has two fates, right? It just doesn't stay in that form. It either gets converted to acetyl-CoA for use by the mitochondria, or it's going to get converted to lactic acid, and then subsequently dissociate into a lactate ion and a hydrogen ion. So in other words, if pyruvic acid can't be converted to acetyl-CoA at the rate that it's produced, even despite sufficient oxygen availability in the mitochondria, then pyruvic acid can accept the hydrogen from NADH. So this pyruvic acid can actually accept the hydrogen ion from NADH to form lactic acid in this reaction catalyzed by LDH, and reform NADH to allow that cycling, or this utilization of G3P and the continuation of glycolysis to occur. Once produced, again, this lactic acid ionizes to release hydrogen ion, which will cause intracellular acidosis, and the remaining ionized molecule is called lactate. So this is often where we come to lactic acidosis. The lactate ion is the signpost, ultimately, of a high glycolytic flux. Again, we'll talk a little bit about it, but the rate of lactate in the blood is ultimately a balance between how much lactate appears in the blood versus how much disappears and is ultimately utilized and shuttled to different muscle cells and active and non-active tissues. We'll talk about that later. But this is kind of the root of this lactic acidosis. And so ultimately, we have this concept that lactic acid is only produced when the cells have insufficient amount of oxygen. But in fact, lactic acid right now, if we measured the lactate levels in your blood right now, lactate's being produced right now. And the amount of lactate in your blood on average would be, say, 1 to 3 millimoles per liter. So even at rest, when the muscle cell and the blood is fully saturated, and intracellular PO2 is probably 40 to 60 millimeters of mercury. So there's tons of oxygen in the cell to run and drive oxidative phosphorylation as a product. Oxygen as a product of oxidative phosphorylation. We're still producing lactate. And that's important because lactate reformation is important because it actually contributes to the recycling of NADH so that glycolysis can continue. If lactate wasn't produced, we would come to a screeching halt because we wouldn't be able to convert or phosphorylate this G3P and produce the ATP. We would have a halting of glycolysis after the energy investment phase. We wouldn't be developing we wouldn't have any of the energy development phase if we just stopped the process at G3P. So we need to recycle this NADH to get it into its NAD form. And lactic acid production or lactate production is a means of doing that. So, in fact, blood lactate levels under steady state conditions, even when the mitochondria are fully saturated with oxygen, there's still lactate being produced. And it's because it facilitates and it allows for glycolysis to continue. So it's not this dead-end byproduct. It's actually an important molecule that's generated because it keeps one of the energy systems active and viable. Okay? So that's it for today, and we will start up again on Tuesday morning. Have a good weekend.